All right, everybody, we're on Explore 4, electron representations. If you take a look here in green, how does the octet rule describe the arrangement of electrons in noble gases? That's the essential question we're trying to answer. So let's go ahead and draw our Cornell note lines. Okay. I'm recording this on Monday, 10/30/23. We'll give ourselves a nice margin section for writing our notes. Our essential question, we're just going to write what we have there. How does the octet rule, okay, oct means 8, right? How does the octet rule describe the arrangement of electrons in noble gases? Question mark. A real quick scan of our text. We can see kind of the topics here. We have the octet rule here, the octet rule. Some vocabulary words, periodic table, octet rule, noble gas, and noble gas configuration. Valence electron, electron configuration. And it really looks like that's the main section there. And then we have, of course, an exploration, which is a sort of simulation. We have a video on valency, an image that you may want to consult. And then we have a video here on the octet rule as well, which I'm going to let you guys watch on your own. And we have a little periodic table. And as you take a look at this periodic table, you can see that the elements seem to be color-coded. So we'll take a look at that as we move through here, okay? So Roman numeral 1, the octet rule. Okay. And what do we want to say here? It's interesting. I highlighted these, but it seems like the highlights have disappeared. Gilbert Lewis, the guy who gave us the Lewis dot structure, he is the one that also gave us this octet rule. He derived the octet rule. And in short, the octet rule states that atoms react with one another in ways that makes their electron configurations the same as that of noble gases. Okay. Okay, so what are we talking about here? Let me come over here and I'm going to open up the periodic table. There it is, ptable.com. And if you take a look at all of the group numbers here, right, we're talking about these things right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, all the way to 18. Okay, remember that this periodic table is your friend. It's going to be very useful for you. The noble gases are the ones that are all the way to the right. So I'm going to go ahead and highlight these right now. All of these guys are your noble gases. And you can see here, look at the color, noble gases. These are your noble gases right here. Okay. So capital A, they occupy group 18, group number 18. If you recall from the old naming, that old name would have been actually the 8A. okay? And if you take a look, what we're saying here is that whether you're talking about helium is kind of an interesting one because helium has an atomic number 2. So on the inner electron shell, which can only have a maximum of 2 electrons, right? Helium can have a maximum of 2. We say that its valence is full, right? It only has 2 electrons. 2 electrons, and the first orbit can only take 2 electrons. Okay. Now, everything else, when you take a look at neon, argon, krypton, xenon, and radon, they all have 8. Okay, and this number here, if you recall, this number 8 here indicates that it has 8 valence electrons. Okay, 8 valence electrons. So here we go. If I come over here, let me just draw a few of these, okay? Neon. Neon has 10 electrons. We're assuming that it's neutral. So if you were to draw it in conventional terms, you would say that neon has in the first orbit 2 electrons, and in the second orbit, it has 1, 2, 3, 4, 5, 6, 7, and 8. What is the maximum number that you can have in the second orbit? 8. Does it have all 8 of them? Yes. So its valence is full. Okay. So let's just write a little note to ourselves here. The second shell has 8 electrons, which is the maximum it can hold. Therefore, the valence is filled, or we say full, right? Now, I guess I can do this just for grins. We also have talked about doing these as quantum models, these electron cloud configurations. And what would that look like? Well, we would say that an neon would have 1 s2. It would also have to fill the second energy level, 2s2, 2p. What would we need here? 2, 4. We need 6 more. Oh, there you go. So that would be neon's electron configuration. And if you were to draw that out, it would look like this. You would have the 1s orbital. You'd have the 2s orbital. You would also have the 2py, 2px, and 2pz. So you'd have in here 1, 2, in here 3, 4, 5, 6, 7, 8, 9, and 10. So that's the way it would look in the quantum model. And we're talking about the highest energy level, which is energy level 2. And what is 2 plus 6 equals 8, right? The same as the 8 electrons in the Bohr Rutherford model. Okay. And you can go on and on. Let's take a look at argon. Okay, we're talking about argon right here. Argon has 18. And because it's in the 8A column, or 18, so remember, in the 18 column, you could use this rule of just saying 18 minus 10 equals 8. Or you just remember 8A. It's in the old numbering was 8A. So you know that the valence is going to have 8. Well, let's run through these, okay? So here's AR. The first orbit can only have 2. 1, 2. The second orbit can have how many? 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus 2 is 10. We need 8 more. So here we do a third energy level. Whoops. So let's draw a third energy level. That too can have a maximum of 8. So 1, 2, 3, 4, 5, 6, 7, and 8. Do these all add up to a total of 16? 8 on the third, 8 on the second. 8 plus 8 is 16, plus the 2 on the inner equals 18. So yes, we have all 18 of our electrons, and we have our third shell has a full valence. All right, I'm not going to continue going down there, but you can do that for krypton and xenon and radon as well. And all of them will have 8 electrons in their outer shell. Lewis found out, kind of came to the conclusion that when you have a full valence, the atom is most stable. It does not want to react with things. It's what he called an inert element or an inert gas, since these are all gases. So I guess we can go ahead and add that to our notes there, okay? Noble gases are inert. That's the word you want to know. That means non-reactive. There are some exceptions, but they're pretty unstable when they do that. And you need to have extremely cold temperatures to get them to react with other things. But for the most part, they're inert, non-reactive. Why? They're happy. They got their 8 valence electrons. They're stable, okay? Let's write this down here. How do I want to write this down? Maybe I want to make this letter A, occupy group 18. Let's go down and make this letter B. Okay, letter B. Elements, and when we say elements, we're talking atoms. Atoms with unfilled valence electrons are reactive. they try to become stable by achieving a full valence. So let's take a look at some examples here, okay? What if we, I'm going to clear my screen over here on the left. What if we go to our 7A electrons? Okay, example. 7A elements. That would be group 17. Okay. If I take a look at something like fluorine, which is number 9, we're going to take a look at this one right here. Okay, we're going to look at fluorine. Fluorine, because it has, it's a 7A element, group 17, it has 1, 2, 3, 4, 5, 6, 7. You can see here that it's missing an electron, missing 1 electron. So the way fluorine is most likely going to react is if it could steal the electron from someone, from another atom, it would have 8 electrons. Okay, so it needs 1 electron to be stable. If it gains an electron, and then it's going to become negatively charged. And the reason why we say that is fluorine is number 9 on the periodic table. That means that's its atomic number is 9. It has 9 protons. Assuming it's stable, neutral, then it has 9 electrons as well. So if it gains 1 more electron, it'll have 10 electrons versus 9 protons. And it'll become negatively charged. And that's what we call a negative ion, an anion. Okay. Let's go ahead and show you how that happens. And the way I'm going to show that is I'm going to pull out another one. Okay. Let's take a look at sodium. Okay, we're going to look at this one over here. Sodium. Sodium is in our 1A group, and it has an atomic number of 11. So I write down sodium. Sodium has 11. So let's go ahead and, but when you take a look at the top number up here, it's in the 1A. So its valence is 1 electron. It has only 1. So the sodium and the fluorine, they can react with each other. And the way that reaction would look is something like this. So we're going to say that the sodium has, and maybe I should draw this, okay? I think that's what I'm going to do here. So I'm going to just erase this guy. Sodium has 11. So we'll say the first one, 2. The second one is 8. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it has 11, so we got to add 1 more. So its valence shell has 1 all by itself. Unstable. Okay, so let's just write that down. 1 electron in its valence, therefore unstable. So what would be easier for sodium? Would it be easier for it to gain 7 more electrons so that it could have 8 electrons in the third shell? Or would it be easier just to give away that third electron? Well, if you give it away, what's going to happen is this. I'm going to just take my eraser. I'm just going to erase this. If we give away the electron here, then we have 8 electrons in the second shell, and sodium is happy. But remember, sodium originally had an atomic number 11. That means it has 11 positive charges, and if it was neutral, it would have had 11 negative charges. If you give away that last electron, it's not going to have 11 anymore. It's going to have 10 electrons. 11 positive versus 10 negative, you have more positive than negative. And so we say that sodium is a positive ion. It has a positive charge. It has 1 more protons than it has electrons. Now, where would that electron go? Well, fluorine and sodium would react very nicely to each other because fluorine happens to need 1 electron, right? Okay, so if we clear my screen over here, take this back. If you recall, fluorine had 9. Okay, fluorine had 9. It had 9 positive protons, and we assume that it had 9 negative electrons. And if you were to draw fluorine out, it would look something like this. The first shell has 2. The second shell can hold up to 8, and it has a maximum of 9 total. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. So see what we're talking about? Count the number of electrons in that second shell. There's 1, 2, 3, 4, 5, 6, 7. It's missing. It's missing 1 electron. In fact, I could just go ahead and erase that and just say it's missing an electron. Would it be easier for it to lose 7 electrons just so it could have a full valence in shell number 2? Because remember the rule, shell number 2 only needs 2. Or would it be easier to gain 1 electron? It would be easier for it to gain 1 electron, for example, from sodium. So you could form a bond here. You could have sodium bond to fluorine. Sodium would give away its electron, and it would become positive. Fluorine would gain the electron, right? It would gain the electron, and by doing that, it would no longer have 9 positives and 9 negatives. It would become 10 negatives. It'd gain 1 electron. And now we would say that fluorine has a negative charge of 1. And this is what we would call an ionic bond. Ionic bond, where the sodium has become charged, the fluorine has become charged. Sodium lost an electron, Therefore, it has one more proton than electrons. It's positively charged. The fluorine now has one more electron than protons. It is negatively charged. Okay, so that's a lot to think about. That's a lot to kind of wrap your head around, but you guys are going to be able to do it. I have no doubts about that. Let's take a look at this picture here. I want you just to understand that these things are organized. Your alkali metals are these guys right here. Okay. Your alkaline earth metals are these guys right here. Your transition metals, what we would call your B group elements, are all over here. Right? Transition metals. And, on and on. We can go and take a look at your noble gases. They're over here. Right? These are your noble gases. And your halogens. Your halogens are right here. And your other nonmetals, and on and on. And these are all based on having similar characteristics. Just like your text says, groups such as these, alkali metals, halogens, noble gases, have similar characteristics. Which characteristic is used when predicting the ion that will form from a neutral atom? Well, a lot of that has to do with the valence number, right? How many electrons you have in the valence. Okay, so let's go ahead and write down letter C over here. Letter B. We're going to say letter C. Okay, and let's just continue with our line here. Okay. And we're going to say that the periodic table groups elements in different, according to similar, characteristics. Okay. i.e., the 8A, which would be number 18. These are what? These are inert gases, what we call your noble gases. They have 8 valence electrons, and they are non-reactive. Non-reactive. Okay, that's an example there. What do they say? The octet rule is a powerful tool for predicting the ions that will form from neutral atoms. It is very consistent for elements in the S and P blocks. Okay, and if you recall, you can hit the electron button over here, and you can see that the P blocks are these guys over here, right? P block. This is your P block. And your S block is over here. And so what that text said was that your this octet rule is very consistent for elements in those areas. Okay. We talked about noble gases. We talked about them being inert. We did talk about them. Um, they can share their electrons. Some noble gases will share their electrons, but what? These compounds are unstable. So this occurs not often, it occurs very rarely and under extremely low temperatures, only at extremely low temperatures. Okay. Well, I think that's about it. All right. So let's go ahead and have you do this. Let's go ahead and write a summary sentence. Okay. And that'll do it for us. All right. Have a great day, guys. Bye bye.